Remember to, at some point this will bite me. All right, everything's set. So, this homework, the one group, like Mike and whoever, right? I guess I messed up your grading, so I have to regrade it. But it's kind of interesting, I guess, and at least to me, that the question, there's like a question that's like, what is it? What's the question like? It's one of these, right?
Last week.
Oh. All right. Sorry. All right. Sorry about that. It's like the 1 and 2 thing, right? Isn't it this?
Yeah.
So 2 is Brownian motion and 1 is ballistic motion. Everybody got that. And then you guys went further and said that 2 is because of Newtonian fluid, which I thought, from my perspective, wasn't right, because you got like the thing, if you wait, so if you say you have a power law fluid, and if you wait long enough, it's going to have random motion, so it'll be Brownian motion. But in the context of time, it isn't true. So depends where you are with respect to the relaxation time. So if you're shorter than the relaxation time of the network that you're looking at, then it's ballistic, because the network looks like a network. It looks like a rubber. So it springs back and pushes the thing. So you have the elasticity, but if you're at a longer time, so if you wait, I mean, I guess I was thinking in terms of infinite time, then it wouldn't matter. So you were right, I was wrong on it, but basically that was my reasoning. So I have to go back and fix that. That brought up this, then I looked in the paper and he says something, so he says linear viscoelastic, or he says viscous and then elastic, right? And then I thought, so anyway, he references this paper by Mason, which I didn't link before, but it turns out like this paper's, all right, it's got 597 citations, I think, something like that. So that's a lot. I mean, usually a paper will get like 10 citations. It's 2000. So it's 22 years ago. So if you divide 500 by 22, it's like 10 or 20 a year, which is still a lot. Anyway, and also it's like a theory paper. So it's like, usually those won't get that many citations, you know? So this Exxon, if you ever take, like there's a highway that goes to Newark, New Jersey, right? And this place is right off it. You can see this Exxon Research Lab. Annandale, New Jersey. Annandale with the name of 2 ducks or something in a pond, Annandale. The town's named after the ducks. But you go through, there's a highway that goes through like Lehigh, Pennsylvania, and then goes to Newark kind of, then eventually to New York City. I forget what that is, but you can see this place is like right to the right-hand side when you drive by. And it's a small place, it's just like one building, which is surprising because it's a lot of like famous people went through there. Anyway, so Mason's there. So I guess Mason worked with White's or something. I don't know the story. White's was at Penn in Philadelphia, and then this isn't too far from there. So anyway, this is a pretty good paper though, actually, if you read it. So he's kind of getting to this equation where or the G. So he's getting to this equation where you have this thing that you can measure, which is the mean square displacement of the particles. You get that from the dynamic light scattering. That comes right out of that. Then you want to get these moduli from it, like particularly you want to get the storage and loss modulus. Oh, the other thing was that people said like Fourier transform and then Laplace transform and got them kind of confused. This paper explains exactly how that works, so it's a pretty good paper and it's fairly clear, but if you read it, you're gonna have to be looking things up while you read it, so it isn't, it's actually, he explains everything in this. Like he pretty much explains like how this whole thing works and how the world fits together. And he even like gives a new derivation for this, what he calls a generalized Stokes-Einstein equation, which means Stokes-Einstein is like KT over the friction factor. And then it's when you put in a friction factor that's got time dependence to it, and a generalized, in other words, wherever that equation is. Like this thing. So basically this, so there's two ways to do this. This F is a Fourier transform of RFT, of this time dependent function you get from the dynamic light scattering. There's the correlation function for position of the beads, if it's a DWS. And then someplace here is the Laplace transform somewhere.
I think anywhere as the S, G of S.
Yeah, G of S, and then the symbol for Laplace is, I forget what it is. It's not F. It's something like a Greek L or something. Yeah, here, this kind of script L thing, so Laplace transform. So the two are both used, and I didn't realize that either. So there's like a couple things I hadn't kind of figured out about this. I'm not really a dynamics person, but trying to be. But so anyway, you have.
Don't forget to.
Oh yeah. All right. Sorry. Everyone has a little man in their mind telling them what not to do, what to do. So that's what you are for me. Like the guy that says, don't run that red light, no matter how much you're in a hurry. See, you can put a weight on something. So you have some rubber or something, you put a weight on it, and then it's going to stretch with time. That's what's called creep. Yeah, the strain goes with time. And the other thing you can do is you can take your rubber and then just pull it a certain strain and then watch the stress change with time. So both will involve. So here, this thing's going to like grow slowly. And here, the stress is going to start out as, so you're applying the pulse strain. And here you're applying the pulse stress. And then here, this thing will decay with that exponential minus 2 over tau thing. But it's 1 minus that, because this is time here. So this is called, these are things I think everyone has experienced in one form or another. So those are the base measurements that these people talk about. If that's kind of what, so if you could, the idea is like if you really want to get, so this is the spectrum of the relaxation spectrum. Every other measurement you do is going to be based on that. That's the idea. Right? So anyway, so in this thing, you can get from, you can botch this up. You can get from the viscosity and the strain rate, which is the change in strain with respect to time, is the stress, the shear stress, shear, and then you can also have the shear modulus times the strain. Again, 1, 2 means you could put in the force that way, and you kind of looking at a change the other way. So it's like force X and whatever the changes in the Y direction. Right? So it's like deck of cards shear. It's not tensile would be like pulling or flip beer and whatever to stretch it. Anyway, so you have these two equations, these two are equal. Then you have this setup, so you have B gamma over gamma, which you can integrate to get X log. And then it's going to be dt. And then the prefactor to that is going to be the modulus over the viscosity, because viscosity is like time. And that becomes 1 over the time constant for the thing. This will give you log gamma equals T over tau, T over tau. And then that gives you, if between the limits of T is 0, you get 1, and whatever T you're at, and then you get this decay thing. So this function is just take the definition of viscosity, definition of modulus, and equate the stresses in the two, then do an integral and get that curve. That's the same kind of thing I did before, but I did it with velocities. Like, so yeah, you do a force balance because so here I'm talking about bulk. So I talk about stress and strain because I have an area that exists that I can, but if you talk about molecules or colloidal particles, there's no area. Like a molecule or an atom doesn't have an area. So you just talk about force balance then. That's the Langevin equation. Langevin equation is a force balance. The forces are the friction factor times the velocity, where we have the viscosity times the strain rate. And the other force is spring constant times the position. Where we had in bulk, you have like the modulus and the strain. So this is strain rate and the strain. So this Langevin balance is the same thing. This is dx, this is d strain. So you end up with the same equation, except that the time constant is the spring constant over the friction factor. Right. So this is like molecular, colloidal. This is bulk. The two things are the same thing. It's just that you have an area where you can get a stress. You don't have an area, so you have to talk about force instead of stress. And stress is more useful than force. Right? Basically, this is what you have if you have molecules. Anyway, so that said, so this whole thing, so there's just one function that you're talking about. This mu of t is going to be the what's it called? Response function. So we just have one response function for material, and from that response function. So I could take this, so say I have a complex material, like I have a melt or a polymer in solution, right? And I have these little beads in it that are moving around. So they're going to be, and they're being subjected to KT in random direction. Right, and temperature fluctuates. So there's all the spectrum of every kind of stress and strain in there, theoretically. Oh, to get this fully described, you have to go from 0 to infinity. Any of these, if you want to do for a transform, you want to do a Laplace transform, then you have to be talking about an integral from 0 to infinity. So in that paper, Mason says, since our relaxation has limits of ballistic motion and Brownian motion, and there's no other options, and those are both power laws and time. So because of that, then you can extrapolate from 0 to infinity, because there's just going to be this power law thing. So you can integrate it. You can just extrapolate whatever power it is. It doesn't have to be 2 and 1, but it can be any power. And as long as it's a power, then you can extrapolate it, and then you can do this integral. Right, so that's one thing he says in that paper, which is kind of useful. I mean, I think these are known things, but he puts it all together in that paper. So he says all this stuff in explicit terms. Like usually people that write theory don't explain things. They just say, obviously, this can be integrated. But he says why it can be integrated. There's still a jump, like you have to understand what he's talking about. There's still a little bit of a jump, but it's much less of a jump than a normal paper. So that's actually a pretty good paper. I think that's why it's cited so much. Anyway, for whatever material you're going to get this kind of decay, it might not be exactly that function. But if you're saying Laplace transform, you're going to do an integral of t of your function, say function of time, then exponential of like t by tau. You're going to sum up a bunch of those. You're going to have a bunch of these decays. You're going to sum together to get the final response to the material. The dt, right? That's the Laplace transform. So that's option A. That's the option mostly used, right? But then in the this is pretty complicated stuff. Like, but it's actually, like, you can see the guy's talking about epoxy, okay, which isn't complicated at all. It's like glue, and it's a sailboard, and it's a surfboard, right? I mean, a sailboat and a surfboard, or a jet fighter, or whatever, right? So it isn't something. The thing he's trying to understand isn't complicated. Somehow it seems to relate to all this other stuff, you know. So I think this happens a lot in polymers. If you start to look at it, you have goo. Like, what are you going to do with this epoxy? It's a pile of goo. And you want it, but you have to manufacture it, you have to use it, you have to understand like how it's going to behave. And quickly you get into this kind of complicated realm of understanding the time and time dependence of how properties are. And you can't get around it. Like, you basically have to go back to talking about, well, there's a general spectrum, and then I'm going to get these properties out of it. You know, so it's kind of a funny thing. So anyway, I mean, normally you try to avoid this if you could, but so anyway, the other thing you can do, so basically the other thing is experimental, right? Because you don't really have, there are some cases where you have an oscillatory. So you basically, he's in the paper, he says you have a cosine that you're applying to it, like your strain or your stress, it's this cosine function, you know, and in that case, it's not going to be this Laplace transform, which is really the natural way to look at this, because the stuff is really going to, you can see, like, if you just talk about viscoelastic, so you have elastic and visco, and then the viscous flow and elastic, but you're going to end up with this Laplace term. You're not going to end up with I frequency time term, which is a swap for the Laplace, right? So this doesn't seem to be natural. Unless you're like the space shuttle, like when it blew up on launch. Okay, that was an oscillatory frequency vibration, more or less, from a rocket engine blasting off at like 30 degrees Fahrenheit, or I think it was 40 degrees Fahrenheit, right? But because of the frequency dependence, this kind of oscillatory frequency, the seals in the solid rocket turned to glass, like they went below the glass transition because it's time temperature, like WLF equation. So there are cases where you're looking at vibrations where the application really is a frequency dependent thing and not just the Laplace sum of these time decays. So anytime you're dealing with a frequency dependence, like tires on the road, every whatever 61 hertz or whatever, I think. Yeah, I figured out what the hertz is for a tire on the highway, but it isn't as much as you think. It's something like five hertz or something. It's not like 1,000 hertz, even if you're going 100 miles an hour. Like, it's, you figure out the perimeter of the tire, it's not such a high frequency. But anyway, there's a frequency spectrum that's being looked at there. So there are cases where that applies. Generally, like, Laplace thinks the right thing. But anyway, so you can break down this same curve, the observation curve, instead of in terms of a bunch of these Laplace decays, you're going to apply like a bunch of sine waves to this. You know, like, so short frequency, high frequency, you sum those sine waves up and you get the same curve. So there's two ways to break down this curve. You can break it down in terms of these exponential decays, that's the Laplace approach, or you can break it down in terms of a bunch of sine waves and they're equivalent. The idea is that they're equivalent. Next, the Cox-Mertz rule. That like time is really one of a frequency. Like you can swap out these two measurements and you get the same information because they're both based on that same response function. And this doesn't, so like this is all mechanical, but this also applies to dielectrics. Exactly the same thing. In fact, this wasn't developed for mechanical, it was developed for dielectrics, dielectric response. for like AC circuits and things. Right, so all the math involved in this, and all the concepts, not this probe idea, but all the basic linear response theory comes from electronics. It doesn't come from mechanics. So people, that makes it even more confusing because you have the compliance, the stress compliance, and the creep. And that becomes like the susceptibility, the electrical susceptibility. So the compliance becomes a susceptibility. And the literature would just call it, you'll find a paper and they just talk about the susceptibility and they talk about a mechanical response of the material. The susceptibility is an electronic AC circuit thing. Right, so they just call it that. And then you're supposed to understand that there's a kind of an analogy going on. Right? So anyway, it's kind of a funny field. The other thing is that it wasn't even electrical people that developed it. It was kind of developed by physicists who were just thinking. They were just thinking about stuff, I think. I'm not sure that they really got a problem they were dealing with when they developed a response theory. And they had the idea like things respond. They can change it into different domains to look at it. I'm not sure exactly how that came about. I think of the original thing because it's too arcane. Like when you look at it, it had to be that they were just sitting around thinking about it, I think.
I know some problems you can kind of only solve by putting it in one domain and then bringing it back out to that full real world domain.
Yeah.
That might be part of it.
Yeah, it's part of a lot of stuff like noise reduction in images. You take the image before you transform it, and you can easily see there's a 60 hertz noise pattern in it that you just get rid of and turn it back into the real domain that's a clean picture. Or whatever the pixel size or something, if you want to clean up images. That's used a lot. It's used in astronomy to get rid of noise and things. Anyway, so yeah, this transform thing has a lot of applications. Once you figure out that you can do it, then someone finds a different way to do it or to use it, so it actually gets to be pretty confusing. It would be nice, I mean, like having a straight pathway. The mechanical thing is pretty simple compared to electronics. So it's like we know, like you can see this physically. You can pull on the thing and watch it stretch, and everyone's experienced that. Like with dough or something, you pull it, it's got some strength, but eventually just droops down and falls apart. Right, so that's creep. And then the stress relaxation is kind of related to that. I think everyone's done this. So anyway, that's the idea. There's two ways to transform it, and it could be Fourier transform. So I graded that one homework. I think I said something about Fourier transform isn't it, and it actually is. It's the part. The Fourier transform is the way that you get the G prime and G double prime, and then Laplace is to convert the real measurement to the. Laplace is for something. I don't know what at this point. Anyway, so that paper is kind of interesting to look at.
We put Fourier transform on the board, but I don't think we had all of that in mind. I think it was by mistake.
Well, okay. Anyway, it turns out he was right. Yeah. So it's like if you read this Mason paper, it's exactly what it's about. Like he says how you can do the Laplace and the Fourier and how the things are related. He explains it. It's really pretty well written, this paper. I don't know. I thought that you must have gotten this paper because it's where he cites it in the other paper, and then I thought you must, because I know you go and look up papers. So, and I didn't give you this paper, so it's partly because it's off track a little bit. It's like maybe too much, but
I think they might also mention Laplace, or not Laplace,
For-
Fourier
yeah.
transforms in the one you did give.
Yeah.
That other one.
yeah, I think so too. Yeah, and this thing.
So I think Laplace domain and Fourier transform is to frequency, but I think the Laplace domain like S is also like an inverse time
Yeah,
domain.
yeah,
So
yeah,
it makes sense that they're both kind of you use both.
yeah. You use both, but anyway, it's good to know kind of why you use both, I guess, and what the Laplace is for, like where it came from. But the Fourier is used everywhere. Like it's used in scattering, but it's used like everywhere because every time. In other words, it's a repeating patterns. If you have something like the stock market, and you know the car prices go up and down, and then the steel prices and whatever. So, and then the total GDP or whatever is going to be based on all that stuff put together. So it's natural to say you're going to Fourier transform it. That's kind of like derivatives trading, I guess. You know, you're going to figure out where things are going to go because you can see that there's a pattern. Each one's a cyclic commodity market, and they all add together into the total GDP. Or you can figure that out for one stock price too, like all their whatever they buy chips from China to make the car, and like the chips, and then like those have cycles. So everything's got a cycle to it. It's like this Intel plant in Columbus, you know, and it's like this is typical commodity business, right? Like it happens in the polyethylene business too. The price goes up, and then all the polyethylene producers go, "Oh boy, we better have more plants," you know. So they all build a bunch of plants, and then and it takes them like 5-10 years to build the plant. So 5-10 years later, boom, like the price drops to nothing. Everyone they fire everybody too. It happens with the jobs too. Like they hire a bunch of people, oh, the price is going up, we got to hire all these people. And Intel does that too, I guess. So it's kind of like the chips are almost like a commodity at this point. And right now we're at the place where the price is high and there aren't enough. And like they're going to build a gigantic plant, and then like 10-15 years from now we find a lot of layoffs and things. Probably, maybe, I don't know.
Or we all have, you know, cell phones that are $50 a piece because the circuit boards and stuff are so cheap.
Yeah, it could be. Yeah, I mean, that'll happen. The price of the cell phone will go up and down too with it. So see, you could do that with the kind of a Fourier transform of the price of cell phones. And I mean, it's got plastic components, so it's related to the polyethylene market. So that you have these different frequency things, and you could just kind of figure out what's going on. If you could identify the frequencies that are going into it and predict how those markets are going to go. Then there's like terminal oil, so all this stuff is connected together. There's also a gradual trend for each of the oscillating frequency things to it. That's what we should be doing anyway. Make tons of money, forget about this stuff. So maybe. In the end, you die, so it's not going to make any difference. So I guess that's the main theme. Everyone ends up in a tie. So that's that business. Hopefully that's all right. Then is that all the stuff that I got you guys on? Or?
There was some other stuff about the different moduli, how they differ. I think how they differ throughout the frequency curve. I don't remember.
My question was where.
I remember, this is Sarah. I remember what that one was, because we had said on the homework that it
Oh, yeah.
was
Right,
the
frequency. Yeah.
we had said the crossover between the moduli was related to an entanglement network formation versus the gel or rubbery plateau, but we didn't explicitly say it was shear thinning, the entanglement network.
Stuff. So it's just not a waste to kind of. I bet there's a way to hide that thing. It's not. There's definitely a way. I don't remember what it is. You have to be in the Zoom thing.
It was an option on there, so like high something.
Yeah,
On that more.
on here. Oh, in here.
Yeah, where you clicked it.
All right.
High floating media controls.
That could be it. Oh, and then when you hit escape, which is also the same thing you do for the, oh, but it leaves that thing up. It's like, all right, so this is some notes on dynamics that are floating in there, but so it's the same kind of thing. And it might be helpful to kind of go through this before the Rouse thing, I guess. So we already know about that. So basically in the Rouse, you're going to take the spring constant that we had for spring constant here so each chain is going to be a spring. So it's going to be, so that came from this linear response theory, the idea that you're going to have a spring. I mean, it's the same thing that, here. You have a spring, whatever that is. And so you have this spring constant and then the position and the friction factor and the velocity. So it's a range of values. You have the force, you gotta do a force balance. K spring times X, and then you're gonna end up with the K spring divided by the friction is gonna be the relaxation time. And for polymers, the K spring is the molecular weight, KT over the molecular weight. N, right? And then this thing is, you say that the coil is a bead. So then you can use Stokes' law. So that's a Zinn model. Right, for the bead thing. Right, so you can get the time constant. This is for a polymer. You can get the time constant that way. So this is just saying like you can get the time constant that way. So if this isn't a fully non-draining coil, then you're going to have like the Rouse model for the viscosity of this thing, which is going to be, it's for the size of this thing. So it's going to be different. The friction factor will be different. And then these are just some pictures of the creep experiment. The same thing, how you get this 1 minus exponential. This is just a picture of how the length changes. So you put a weight on the thing at 0. There's an initial jump, right? So it's got this kind of instantaneous jump, and then there's the creep associated with it. So you can break that down into 2 parts if you want. And then the recovery is going to be an instant jump and then a slow recovery. So there's kind of 2 parts. The time dependent part you're interested in is the part that isn't the jump. Right. And then this, you'll see this Cox-Mertz rule mentioned, but it's basically kind of that you can take the Laplace and the Fourier transform and kind of describing the same thing in terms of this response function. And the response is going to be to a delta stress that you put on the material. So you put a delta stress and then you look at the decay of it. This is a creep response function. So, and then there's this, the idea like Boltzmann superposition is that you can break a continuous curve into these component parts that represent either that Laplace term or the Fourier term. So somehow you're going to break down complex responses into individual time constants. And then let's see. So we got, this is the stress relaxation thing. So you have a fixed strain and you watch the stress change. You get a modulus that's time dependent. And then the creep is that you have a fixed stress and then you watch the strain decay. So it gets longer as it stretches out. And then that's called a compliance. So the compliance is kind of 1 over the modulus. I mean, in normal terms, if it's not time dependent, the compliance is 1 over the modulus. But if it's time dependent, then they're related by a kind of a complex function because one of them involves kind of flow. There's flow and solid involved in it, so it's a complex number. So it's not going to be just the inverse of it. Right. So basically, these 2 are related by complex numbers. So anyway, in dynamic, you're looking at it like some kind of so the exponential is sine omega t, 2 pi. You can put a 2 pi in here if you want, but sine omega t minus I cosine omega t. This exponential I omega t expands into that sine plus I cosine. So it's basically a sine wave. Like when you see an exponential I omega t for a wave, that means it's a sine wave. Like you're looking at it just an oscillation. So you're applying here a stress that's oscillating. You're looking at the strain response. And the strain is out of phase with the stress. You can also apply a strain and look at the stress response, but So the applied stress is here, the response strain is here. This is in omega t. So if you multiplied this by 360 degrees or by pi, 2 pi, then this would be, I'm not sure it's 510. So this should be unitless. Oh, well, there's a wavelength. It would be omega t divided by like the wavelength of this thing, right? So anyway, so basically there's a shift. And if this is then shifted and where it's 360 for one cycle, so whenever this goes back to here, that would be 360 or 2 pi, then this del would be an angle, like a phase angle shift. So you have a phase angle shift describes the response of the thing. I mean, there's a straight modulus, like the stress over the strain gives you a modulus. So there's a prefactor that's a modulus, but the response is guided by this del, the shift factor, the shift in the angle. Right. So, and if the modulus, so you see like tan delta is what we talked about. That's the same del. Like tangent of that delta gives you the storage over the loss. The loss. So if this thing's a Hookean elastic, these two, so the del is 0. Right. The two would be exactly the same. And if it's a viscous element, these two are, so it's completely there's complete loss of the energy that you put in it. There's no result. Like you push it and it just stops. So there's nothing has been done, right? Heat has been given off. So it's completely lost, right? So it's basically in that case, this thing shifted by 90 degrees. So the peak here comes at the 0 there. So just 90 degree shift in it. So del is 90 degrees. So in between del is some other number between 0 and 90 degrees. Like those are kind of the options. So anyway, Hookean elastic, it's in phase, totally in phase. Newtonian fluid, totally out of phase. Right, that's the idea of this thing. So then you have like this viscous. Then you have this kind of viscous relaxation response, right? That I said before. So you do like just a balance of MA and the friction factor, and you can get this exponential response in the thing, right? So that we got before. And then this is just saying, this is from a book by Doi. So he's saying that for a polymer coil in solution, like this relaxation time, which is going to be the Stokes over the viscosity of the water, say in water, is like almost 0, like it's instantly moving. So this tau number is 0. So the thing ends up being like this correlation function for a polymer coil in solutions, like a delta function. So you just get the diffusion coefficient from this. That's used later. So that's used later in this stuff. So this is let's see. So this is basically this same balance, friction factor times velocity. So you've divided by the friction factor. And then this is the change in energy. So change in energy dx is the force. This is just the force. The change in energy dx is the force. So that ends up being just you can get the spring constant for that if you want. It's x squared times k spring if you do that. So this shouldn't be harmonic oscillator. Oh, that can't be changed. This is actually, so this expression is for the viscous decay. The harmonic oscillator has like a sine wave in it. This isn't the right answer for this thing. I mean, this isn't the right title on this thing. I don't know why it's there like that. This is just plugging in the numbers to get that same expression, that over tau to get the, so we've already kind of done this. What else is in here? Yeah, I can see why I skipped over that. So, yeah, so generally they talk about this primary response function. So you apply a stress, get the strain, or you get the motion, you apply a force, get the motion. Then that thing can have these responses. I showed you that before. This is that exponential decay thing. So that's the Laplace transform. Then this is hooking elastic. So you pull it and it immediately, when you release it, it immediately responds. It's the same as the input, like input equals output. And for a viscous element, you push it and it just stays there. Then to get the final thing, you integrate that. Right, so you can get, this is kind of based on these two ideas, right? Superposition and then causality means that before, so you can start at a time 0 and there's nothing, there's no pass to it. And then everything that happens after that is summing up all the events that you did to it. And then times this response function. And if you sum those all up, you'll get what's happening now, like how it responded. Like what is the position of the thing? So you're like kicking it in time with some odd function. Every kick is going to be like integrated across all time in terms of the response function, and you end up with this thing. So it means that it's all the kicks are kind of independent and they just sum together, superposition, and then the cause and response, like it's a constitutive response. It's gonna, the constitution of the thing leads to a response from whatever perturbation you put on it. Anyway, this is kind of what that paper goes through, that Mason paper. Not sure what else we need to say about this. I think we don't need this right now. He mentions a Kramer-Kronig relationship, but it's just how you can get, how you can kind of convert, how you can describe the frequency dependent of the storage and loss terms in terms of the frequency, just in terms of the frequency and the relaxation time. So I don't want to go through that now. All right, that's that. And now, what else do we have going on? I'm missing. This thing. Yeah, so this is. I think I'm just going to quit here for today, and we can go through this next week, like the Rouse model, because I haven't really done all this, gone through this stuff that much yet. Not sure why, but I just didn't have time this week somehow. So anyway, why don't we call it quits there for today, you know? And yeah, I'll dig up a paper on some of this stuff. Hopefully it'll be different than last week's paper. Probably be like more viscoelastic, like rheology type thing than doing this. So, and that should be okay, I think. Right. I'll fix the grades on that homework. Like I messed it up. I was thinking, and I looked at it, and you guys were right. So I have to fix that. Oh, I know.